June 27, 1942. Midway Atoll, United States Pacific Territory. The late afternoon sun cast long shadows across the coral runway as Commander Fuchida Mitsuo limped toward the wreckage of Boeing B-17E serial number 41 to 9234. His left leg, badly burned during the carrier battle 4 weeks earlier, protested with each step, but professional curiosity drove him forward. The massive bomber had crash-landed on Eastern Island 2 days prior after sustaining catastrophic damage from Japanese Zero fighters during a reconnaissance mission. What remained of its tail section bore the tactical number of the 11th Bombardment Group. Fuchida had led the first wave of carrier aircraft against Pearl Harbor 7 months earlier. He had coordinated the attack on the American Pacific Fleet with precision that changed the strategic balance of the entire war. Yet standing before this wrecked American bomber, studying the construction methods visible through torn aluminum skin and exposed structural members, he experienced something unexpected, a cold recognition that Japan had entered a contest it could not win through courage or tactical brilliance alone. The Boeing aircraft before him represented industrial capability on a scale that Japan's factories could never match. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The realization did not come from the bomber's obvious features like its defensive armament or bomb capacity. Instead, it emerged from subtle details visible in the wreckage. The precision of riveting patterns, the standardization of components, the sophisticated manufacturing techniques evident in every structural element. This aircraft was not the product of skilled craftsmen carefully assembling a single machine. It was the product of an industrial system designed to produce thousands of identical machines, with minimal variation. Fuchida understood aircraft construction. He had visited Japanese aircraft factories. He knew how Mitsubishi built the Zero fighters and how Nakajima assembled the Kate torpedo bombers that had struck Pearl Harbor. Japanese production relied heavily on skilled workers who fitted components individually to each airframe. Master craftsmen formed aluminum panels by hand. Experienced technicians adjusted parts to achieve proper fit. No two aircraft were truly identical because each represented the accumulated judgments of dozens of skilled workers adapting materials to specific requirements. The American bomber told a different story. Panels appeared to have been formed by mechanical dies rather than hand-shaped by craftsmen. Rivet holes aligned with machine precision. Structural members showed dimensional consistency that suggested automated fabrication rather than individual cutting and fitting. Even in its destroyed state, the bomber revealed systematic mass production methods that Japanese industry had not achieved. The aircraft's presence at Midway represented more than just military hardware brought to a combat zone. It embodied America's industrial response to Pearl Harbor. In December 1941, the United States possessed fewer than 200 heavy bombers of all types. By June 1942, production had accelerated dramatically. Boeing factories in Seattle were delivering completed B-17 seconds at rates approaching 1 aircraft per day from a single production line. Additional production lines were being established at plants in California and Georgia. The industrial mobilization was just beginning. American factories were being converted from civilian production to military manufacturing. Automobile plants were being retooled to build aircraft. Machine shops were shifting to weapons production. The arsenal of democracy that President Roosevelt had promised was taking physical form in factories across the American continent. Within 18 months, Boeing and its licensees would be producing more than 100 B-17 heavy bombers per month. Within 2 years, monthly production would exceed 300 aircraft. By war's end, total B-17 production would surpass 12,000 aircraft. Japan's entire heavy bomber production across all manufacturers would never exceed 1,500 aircraft for the war's duration. The disparity was not primarily about design superiority. Japanese engineers could design capable aircraft. The Mitsubishi G4M bomber, though vulnerable to defensive fire, possessed remarkable range. The Nakajima B-5N torpedo bomber had proved devastatingly effective at Pearl Harbor. Japanese aircraft designers understood aerodynamics, propulsion systems, and combat requirements. The fundamental gap lay in production methodology and industrial capacity. American factories were organized around principles of mass production that had been refined through decades of experience in the automotive industry. Henry Ford's assembly line techniques had revolutionized manufacturing in the early 20th century. By the 1940s, those methods had matured into comprehensive production systems that could be applied to complex products like aircraft. The Boeing production system broke aircraft construction into thousands of individual operations performed by workers with specialized training in specific tasks. Components were manufactured to precise tolerances that ensured interchangeability. Assembly lines moved aircraft through sequential workstations where trained teams installed specific systems. Quality control was systematic rather than dependent on individual craftsman judgment. The entire approach was designed to enable rapid production using workers who could be trained in weeks rather than requiring years of apprenticeship. Japanese aircraft production retained many characteristics of traditional craftsmanship. Skilled workers held significant authority in determining how components should be fitted. Production rates were constrained by the availability of experienced craftsmen. Training new workers required lengthy apprenticeships under master craftsmen. Quality depended heavily on individual skill rather than systematic processes. The Japanese system produced excellent aircraft when sufficient skilled labor was available and time constraints were minimal. Under wartime conditions requiring rapid expansion of production, the system revealed fundamental limitations. Training new workers took too long. Production could not scale beyond the available pool of skilled craftsmen. Quality became inconsistent as factories attempted to increase output by employing less experienced workers. The strategic implications extended beyond simply building more aircraft. Standardized production enabled efficient supply chains and field maintenance. An American B-17 damaged in combat could be repaired using parts manufactured anywhere in the United States production system. Components were precisely interchangeable. A cylinder from one engine would install directly into another without adjustment. A hydraulic pump manufactured in California would fit an aircraft assembled in Seattle. Japanese aircraft required more complex logistics. Parts often needed adjustment before installation. Repairs demanded skilled technicians who could adapt components. Supply chains had to account for variations between aircraft produced by different manufacturers or even from different production runs at the same factory. These differences seemed minor in peacetime. Under combat conditions, with damaged aircraft requiring rapid repair to return to service, standardization proved decisive. American air units could restore damaged aircraft to flight status quickly. Japanese units struggled with longer repair times and required more skilled maintenance personnel. The Boeing B-17 at Midway had carried a crew of 10 men. The aircraft commander, co-pilot, navigator, bombardier, flight engineer, radio operator, and 4 gunners. Each crew member position required specialized training. American military aviation training systems were organized to produce aircrew in large numbers using standardized curricula. Pilot training followed systematic progression from basic flight school through advanced training and finally to type-specific instruction on heavy bombers. Navigator training employed sophisticated equipment and standardized procedures. Gunnery training used consistent methodologies across all training bases. The systematic approach enabled the United States to train tens of thousands of aircrew during the war years. Training capacity expanded to match aircraft production. New air bases were constructed specifically for training purposes. Civilian airports were converted to military training facilities. The entire system was designed around the recognition that modern aerial warfare required not just excellent individual pilots, but large numbers of adequately trained crews. Japan approached aircrew training differently. Pilot training emphasized individual skill development over standardized procedures. The most capable pilots received extensive training lasting years. Less capable candidates were weeded out early. The result was a cadre of exceptionally skilled pilots at war's beginning, but the training system could not rapidly expand to replace losses. When experienced pilots were killed in combat, replacing them with equally capable aviators proved impossible within acceptable timeframes. The strategic consequences became apparent as the war progressed. American air units could absorb heavy casualties and rebuild strength through systematic replacement of aircraft and crews. Japanese air units suffered permanent degradation when experienced pilots were lost. By mid-1943, the quality gap between American and Japanese aircrew would reverse completely as Japanese training programs struggled to produce minimally qualified pilots, while American programs continued delivering well-trained crews. The bomber wreckage at Midway represented all these interconnected systems. The aircraft itself embodied industrial mass production. Its crew had been trained through systematic military education programs. Its presence in the Pacific resulted from logistical systems that could transport men and machines across thousands of miles of ocean. Its operational employment reflected doctrine developed through careful analysis of bombing effectiveness and defensive tactics. Behind all these visible elements stood the American industrial economy mobilizing for total war. Fuchida understood naval aviation combat. He had studied tactics and operational planning extensively. Standing before the wrecked B-17, he confronted industrial realities that transcended tactical considerations. Japan had initiated war against an opponent whose factories could build aircraft faster than Japanese forces could destroy them. The mathematics of industrial attrition favored America overwhelmingly. Every B-17 shot down over the Pacific could be replaced within days by another aircraft rolling off a production line in Seattle or California. Every crew lost could be replaced by graduates from training programs producing thousands of new aircrew quarterly. Japan possessed no equivalent capacity. The Imperial Japanese Navy had entered the war with approximately 400 combat-ready carrier aircraft and 2,000 land-based aircraft. These represented virtually Japan's entire production capacity accumulated over years. Replacing losses required months because production rates could not keep pace with combat attrition. This fundamental disparity would determine the war's outcome, regardless of tactical victories or defeats in individual battles. The Battle of Midway 4 weeks earlier had confirmed Japan's tactical limitations. 4 fleet carriers lost in a single day had effectively ended Japan's offensive capabilities in the Pacific. But even had Midway been a Japanese victory, the underlying industrial equation would have remained unchanged. American shipyards were building aircraft carriers at rates that would eventually deliver more than 100 carriers of all types during the war. Japanese shipyards would complete fewer than 20 carriers. The same industrial disparity that governed aircraft production applied to shipbuilding, weapons, manufacturing, and every other material aspect of warfare. Standing in the fading tropical sunlight examining American bomber wreckage, Fuchida Mitsuo grasped what many in Tokyo would not acknowledge for years. Japan was fighting an industrial power whose production capacity exceeded Japan's by an order of magnitude. Tactical skill could delay defeat. Strategic brilliance could achieve temporary advantages. But absent some dramatic change in the fundamental balance of industrial capabilities, Japanese defeat was mathematically certain. The war would continue for more than 3 years after Midway. Millions would die in combat across the Pacific. Cities would burn. Entire populations would suffer. But the outcome was determined by production capacity, training systems, and logistical infrastructure that favored America so completely that Japanese victory had become technically impossible by mid-1942. The realization brought no satisfaction to Fuchida. He was a warrior, not a factory manager. His expertise lay in tactics and operational planning, not industrial economics. Yet he could not ignore the evidence before him. The precision riveting, the standardized components, the sophisticated manufacturing techniques visible in the bomber's wreckage told a story that transcended individual combat encounters. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. Japan had initiated conflict with an opponent who could replace losses faster than they could be inflicted. The mathematics permitted no Japanese victory without fundamental changes to America's industrial capacity. Changes that Japan had no capability to impose through military action. The coral runway beneath his feet represented American engineering capability, applied to creating military infrastructure in the middle of the Pacific Ocean. The fuel, ammunition, food, and supplies that supported air operations at Midway had been transported across thousands of miles of ocean by American cargo vessels and naval support ships. The entire operation represented logistical complexity on a scale that Japan struggled to match even in home waters. American forces were projecting industrial capacity halfway around the world and sustaining military operations at tempos that Japanese forces could barely match adjacent to their own territory. The strategic implications became clearer with each detail examined. Japan could win tactical victories. Japanese forces could inflict casualties and sink ships. But America possessed the capacity to absorb those losses and continue operations at increasing scale. This was not a war that Japan could win through courage or tactical brilliance. It was an industrial competition, and Japan had entered that competition with completely inadequate productive capacity. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The evening shadows lengthened across Midway's airstrip as Fuchida turned away from the bomber wreckage. His analysis would go no further than his personal diary. The Imperial Japanese Navy did not welcome strategic assessments that suggested inevitable defeat. Admirals in Tokyo preferred reports emphasizing Japanese courage, tactical innovation, and fighting spirit. Industrial capacity was dismissed as secondary to warrior virtues. This institutional blind spot would cost Japan dearly in the years ahead. But in June 1942, with Japanese forces still occupying territory from Burma to the Central Pacific, acknowledging industrial inferiority amounted to defeatism. Fuchida kept his observations private, sharing them only with close associates who understood the military's political constraints. The bombers would continue flying, more would be shot down, more would crash land on Pacific islands, and Japanese engineers would eventually examine them in detail, reaching conclusions that confirmed everything Fuchida had recognized from studying a single wrecked airframe at Midway. But by the time official recognition of industrial inferiority reached Tokyo's decision-makers, Japan would have lost the initiative completely. The window for negotiated settlement would have closed. The only remaining options would be continued resistance, leading to eventual destruction, or immediate surrender, accepting total defeat. Fuchida's private recognition in June 1942 represented knowledge without power. He understood Japan's strategic position but possessed no authority to alter national policy based on that understanding. The war would run its course according to dynamics set in motion at Pearl Harbor. Industrial capacity would determine outcomes, and Japan would lose. The technical examination of captured B-17 bombers by Japanese engineers began in earnest during the spring of 1942. At Clark Field in the Philippines, Japanese forces discovered wrecked B-17D bombers among the devastation left by their initial attacks on December 8, 1941. Engineers from the GICAN, the Army Aviation Technical Research Institute, arrived hoping to find clues about American equipment. What they discovered among the wreckage would initiate a process of industrial awakening that would fundamentally challenge Japanese confidence. In March 1942, as Japanese forces completed their conquest of Java, engineers found 15 B-17E bombers at various airfields across the Dutch East Indies. These represented a significant upgrade from the D model. The E variant incorporated improvements to defensive armament and structural design that made it considerably more capable than earlier versions. At Midway Field, engineers found B-17E serial number 41 to 2000, 471 inches, good condition, aside from missing nose section and engines. The aircraft had belonged to the 7th Bomb Group and had been abandoned by its crew after a crash landing on February 8, 1942, at Yogyakarta Airfield. Japanese technicians faced substantial challenges in restoring captured bombers to flying condition. The B-17E represented advanced American aviation technology. Its systems were more complex than anything in Japanese service. Electrical systems operated on different standards than Japanese aircraft. Hydraulic components used different specifications. Engine installations followed American design philosophy rather than Japanese practice. Using parts salvaged from multiple damaged B-17 seconds and employing captured Dutch mechanics who had been pressed into service, Japanese engineers began the painstaking work of restoration. The process required months of effort, as technicians learned American engineering practices through direct examination and captured technical manuals. The work proceeded slowly, but systematically. Engineers photographed every component before disassembly. They measured structural members and documented construction techniques. They studied wiring diagrams and hydraulic schematics. Every aspect of American bomber design underwent careful analysis. The goal was not merely to restore aircraft to flying condition, but to understand the industrial methods that had produced them. By the end of 1942, 2 B-17 seconds had been rebuilt and flight tested in Java. A third aircraft, a B-17D captured at Clark Field, had already been flown to Japan earlier in the year after. Similar restoration work. The decision to transport restored bombers to Japan for comprehensive evaluation reflected the strategic importance Japanese military authorities placed on understanding American aviation capabilities. Elaborate flight plans were prepared, routing the bombers by way of Singapore and alerting air defense systems along the route so they would not accidentally be shot down. Escorted by fighters, and with a Nakajima-built transport acting as mothership, the B-17 seconds reached Tachikawa Air Base in May or June 1943. The arrival marked the beginning of the most comprehensive technical evaluation Japanese forces would conduct on any captured American aircraft. Major Kazuyuki Saito of the Imperial Japanese Army Air Force headed the evaluation team at Tachikawa, assisted by Lieutenant Shioyama, Lieutenants Second Class Kurusu and Ohara, and Army Assistant Engineer Shimamura. Major Uno and Captain Yagi served as test pilots, while Army Engineer Kaneko conducted detailed studies of the engines. The team's assignment was comprehensive. Every system would be tested, every component would be examined, every manufacturing technique would be analyzed. The examination would reveal not just what America had built, but how America had built it. The structural analysis began immediately. Engineers removed panels to expose internal construction. They measured rivet spacing across multiple airframes. They examined skin thickness and structural member dimensions. They analyzed joining techniques and stress distribution methods. What emerged from this systematic examination proved deeply troubling. The consistency of construction across all three captured aircraft was remarkable. Rivet holes aligned precisely between different airframes. Structural components appeared interchangeable without adjustment. Panel forming showed identical characteristics across multiple examples. This was not traditional aircraft construction as Japanese engineers understood it. Japanese aircraft production relied heavily on skilled workers who fitted components individually to each airframe. Master craftsmen formed aluminum panels by hand, adjusting contours to achieve proper fit. Experienced technicians measured and adjusted structural members during assembly. No two Japanese aircraft were truly identical, because each represented the accumulated judgments of dozens of skilled workers adapting materials to specific requirements. Repairs in the field required skilled technicians who could modify replacement parts to match the specific aircraft being serviced. This approach produced excellent aircraft when sufficient skilled labor was available and time constraints were minimal. The American bombers told a fundamentally different story. Panels appeared to have been formed by mechanical dies rather than hand-shaped by craftsmen. Structural members showed dimensional consistency, suggesting automated fabrication rather than individual cutting and fitting. Even the smallest components demonstrated precision manufacturing that eliminated the need for skilled adjustment during assembly. The implications were staggering. American factories were organized to produce aircraft using workers who could be trained in weeks rather than requiring years of apprenticeship. Components were manufactured to precise tolerances that ensured interchangeability. Assembly lines moved aircraft through sequential workstations where trained teams installed specific systems without requiring master craftsman skills. The engine examination provided even more dramatic evidence. The Wright R-1000 820 Cyclone radial engines powering the B-17 consisted of hundreds of precisely machined components. Engineers disassembled engines completely, measuring clearances and tolerances throughout. Every component was machined to tolerances measured in thousandths of an inch. Crankshafts, connecting rods, cylinder barrels, pistons all showed identical dimensions across. different engines. The maintenance manuals confirmed what physical examination suggested. American mechanics in the field were expected to replace major engine components without any fitting or adjustment. A cylinder from one engine would install directly into another engine. A crankshaft was a crankshaft, precisely interchangeable with any other of the same model. Japanese aircraft engines required skilled assembly by experienced technicians. Components were often hand-fitted to achieve proper clearances. Field maintenance demanded highly trained mechanics who understood how to adjust and modify parts. The American system eliminated the need for such specialized skills by ensuring that precision was built into the manufacturing process itself. The hydraulic system, the electrical system, the propeller mechanisms, every major aircraft system demonstrated the same principle. American factories had achieved systematic mass production using standardized components manufactured to precise tolerances. Major Saito compiled his findings in detailed technical reports that circulated through Japanese military aviation commands. The reports documented American construction methods with scientific precision. They included measurements, photographs, and technical drawings. They analyzed manufacturing techniques and production methodologies. The conclusions were unavoidable. America had organized its aircraft industry around principles of mass production that enabled rapid manufacture of complex machines using less skilled labor than Japanese methods required. The strategic implications extended far beyond aircraft construction. If American factories could produce complex bombers using systematic mass production, they could apply the same principles to every other category of military equipment. Tanks, artillery, ships, vehicles, all could be manufactured at rates that Japanese industry could not match. The production statistics confirmed what technical examination suggested. In 1944 alone, the United States built more aircraft than Japan produced throughout the entire war. American factories would eventually produce approximately 300,000 military aircraft during the war years. Japanese production, across all manufacturers, would total approximately 65,000 aircraft for the war's duration. The disparity was not 10% or 20%. It was nearly 5-1 in America's favor. The weight disparity proved even more dramatic. American industry produced approximately 1,100 million pounds of airframe weight, including spares, while Japanese production may be reliably estimated at little better than 100 million pounds. America was producing more than 10 times as much aircraft by weight as Japan. A large part of American production totaled some 97,810 units, composed of multi-engine bombers, whereas only 15,117 Japanese planes were bombers. America was building heavy four-engine strategic bombers at industrial scale. Japan was primarily building single-engine fighters. The aircraft composition revealed strategic priorities shaped by industrial capacity. Single-engine fighters constituted almost 50% of Japanese production in 1944, more than double the 21% produced in 1941. As the war turned against Japan, production shifted increasingly toward defensive aircraft. Strategic bombers required industrial capacity that Japan simply did not possess. America could afford to build specialized long-range heavy bombers because its factories could simultaneously produce fighters, transports, trainers, and every other category of aircraft in quantities sufficient to meet all operational requirements. The Japanese engineers examining B-17 seconds at Tachikawa understood that they were studying not just an aircraft but an entire industrial system. The bomber represented American manufacturing philosophy made tangible in aluminum and steel, overwhelming capability through volume of production, standardization through precision manufacturing, interchangeability through systematic quality control, rapid production through division of specialized labor, all designed to enable factories to build complex machines quickly, using workers who could be trained in weeks rather than requiring years of apprenticeship. This represented industrial organization on a scale that Japan had never achieved and could not replicate under wartime conditions. The training implications proved equally troubling. American factories were organized around assembly line techniques refined through decades of automotive manufacturing experience. Workers performed specific tasks repeatedly rather than crafting entire assemblies. This enabled rapid training of new workers. Factory output could scale by hiring and training additional workers rather than waiting for craftsmen to complete lengthy apprenticeships. Between 1940 and 1944, American aircraft manufacture transformed from a handwork to a mass production industry, with output increasing 16-fold. Japanese industry retained many characteristics of traditional craftsmanship throughout the war. Production rates were constrained by the availability of experienced craftsmen. Training new workers required lengthy apprenticeships. Quality depended heavily on individual skill rather than systematic processes. The supply chain implications compounded Japan's industrial disadvantages. Mitsubishi Heavy Industries organized many suppliers to provide aircraft parts to its plants, but quality control and dimensional consistency proved problematic across the subcontractor network. In the final stage of the war, destruction of the supplier network by strategic bombing and an earthquake caused the collapse of aircraft production. American standardized production enabled efficient supply chains. Parts manufactured anywhere in the production system would fit any aircraft of the same model. Japanese production required more complex logistics to account for variations between manufacturers and even between different production runs at the same factory. The realization that Japan had entered an industrial competition it could not win spread gradually through Japanese military and technical communities. Engineers who examined the B-17 seconds understood the implications immediately. Military commanders took longer to acknowledge what the evidence demonstrated. Political leaders resisted accepting that Japan's industrial base was fundamentally inadequate for sustained total war against America's production capacity. The captured bombers at Tachikawa became unwitting teachers of lessons that Japanese leadership preferred not to learn. By 1944, the strategic situation had deteriorated beyond redemption. American submarine warfare had severed Japanese supply lines. Strategic bombing was destroying Japanese industrial capacity. The Nakajima plant at Musashino, the Mitsubishi facilities at Nagoya, and the Kawasaki factories all suffered severe damage from precision bombing. An earthquake in January 1945 compounded the damage to Mitsubishi's supplier network, and the combination of bombing and earthquake collapsed Japanese aircraft production. Monthly output fell from over 2,500 airframes in May 1944 to barely 1,500 by early 1945. The decline continued through the final months of the war. The captured B-17 seconds examined at Tachikawa were destroyed in the war's final months. American reconnaissance photographed one late in the war, codenaming it Tachikawa 105 after the aircraft's wingspan, but not correctly identifying it as a captured B-17 until after the war. The bombers that had taught Japanese engineers so much about American industrial methods were eventually eliminated by the very bombing campaign they had been studied to counter. The irony was complete. Aircraft captured to understand American capabilities were destroyed by the industrial system they had revealed. After Japan's surrender in August 1945, the conclusions that perceptive Japanese engineers had reached through examining captured B-17 seconds were confirmed by comprehensive American assessments. The United States Strategic Bombing Survey teams toured Japanese aircraft factories, documenting production methods and assessing industrial capabilities. American engineers observed skilled craftsmen hand-forming aluminum panels that would have been die-stamped in American factories. Manual riveting predominated where American factories used automated riveters. Individual fitting and adjustment were common, where American factories used precision-manufactured interchangeable parts. The survey concluded that Japanese aircraft factories had been organized appropriately for producing hundreds of aircraft. American factories had been organized for producing hundreds of thousands. The lessons learned from examining captured American aircraft influenced Japan's post-war industrial development profoundly. Engineers who had documented American production methods during the war brought those lessons to Japan's reconstruction efforts. They understood that matching American industrial capability required not just copying American products, but implementing American production systems. The transformation required 2 decades. Japanese factories that had relied on skilled craftsmen reorganized around precision machinery and automated processes. Industries that had valued individual craftsmanship learned to value systematic efficiency. Manufacturing that had been organized as collections of skilled workers evolved into integrated production systems. By the mid-1960s, Japanese factories were producing automobiles and electronics using automated production methods comparable to American factories. By the 1970s, Japanese manufacturers had refined those methods, developing production systems like Toyota's just-in-time manufacturing that improved on American mass production techniques. Companies like Toyota, Sony, and Honda became global leaders by combining Japanese attention to detail with American systematic production methods. The quality that Japanese products became known for resulted from production systems designed to build quality into the process rather than relying on skilled workers to individually craft quality products. The story of Japanese engineers examining captured B-17 bombers became a case study in Japanese engineering schools. It illustrated how examining an opponent's products could reveal fundamental principles of industrial organization. It demonstrated that success required understanding not just what competitors produced, but how they produced it. The captured bombers had taught Japanese engineers that modern industrial warfare was won not by superior craftsmanship, but by superior production systems. Not by building better individual aircraft, but by building adequate aircraft in overwhelming numbers. Not by skilled workers, but by systematic processes that enabled less skilled workers to produce precisely manufactured products rapidly. The Boeing B-17 Flying Fortress served as teacher to its enemies. The lessons proved devastating during wartime, but transformative afterward. Japanese industry emerged from post-war reconstruction as one of the world's most efficient manufacturing systems, built on principles learned partly from examining enemy equipment during the war. The engineers who had measured rivets and documented production methods in 1943 and 1944 became architects of Japan's industrial rebirth. They had learned by examining aluminum and machinery that modern industry belonged not to those with the most skilled workers, but to those with the most effective production systems. The recognition that Japan had already lost the war came at different times for different people. Fuchida Mitsuo understood it in June 1942, studying bomber wreckage at Midway. Japanese engineers at Tachikawa understood it in 1943, examining systematic mass production methods they could not replicate. Japanese military commanders understood it in 1944, watching their industrial base collapse under sustained bombing. Japanese political leaders understood it in August 1945, accepting unconditional surrender after atomic weapons demonstrated America's technological superiority in the most devastating manner possible. But the fundamental truth had been visible from the beginning to anyone willing to examine the evidence objectively. America possessed industrial capacity that exceeded Japan's by an order of magnitude. American factories could produce military equipment faster than Japanese forces could destroy it. American training systems could replace casualties faster than combat could inflict them. American logistics could sustain operations at tempos that Japanese forces could barely match adjacent to their own territory. The captured B-17 seconds were simply one particularly clear window into industrial realities that governed the war's ultimate outcome. The defensive armament was impressive. The bomb capacity was formidable. The structural toughness was legendary. But the real weapon was the industrial system that could build these complex machines at rates exceeding one per day from a single production line. Multiply that by multiple production facilities. Sustain that output for years, and simultaneously produce every other category of military equipment in proportional abundance. Japanese forces fought with courage and determination throughout the Pacific War. Individual Japanese pilots and soldiers achieved remarkable tactical successes. But courage could not overcome systematic, industrial inferiority. Tactical brilliance could not compensate for production disparities, measuring 5-to-1 in aircraft and 10-to-1 in airframe weight. Determination could not replace factories destroyed by bombing or supply lines severed by submarines. The war was an industrial competition, and Japan had entered that competition with completely inadequate productive capacity. The examination of captured B-17 bombers at Tachikawa revealed this truth with scientific precision. Every measurement documented American advantages. Every system analyzed emphasized American superiority in production methodology. Every technical report confirmed the same inescapable conclusion. America possessed industrial capacity that Japan could never match through any realistic means. The defensive firepower was impressive and merited respect. The productive capacity behind it was overwhelming and ultimately decisive. That was the real lesson of the captured flying fortresses. Japanese engineers who inspected the B-17 realized they had already lost, not because the aircraft was invincible, but because the industrial system that produced it was unstoppable. The bombers came in their thousands, the bombs fell on their targets, and Japan fell with them. The lessons encoded in aluminum and steel did not end with Japan's surrender. The captured B-17 bombers destroyed in 1945 had taught their final lesson, but the knowledge they imparted lived on in the minds of engineers who had studied them so carefully. Those engineers understood something that took America decades to fully appreciate. Industrial competition was not won by building better individual products. It was won by building better production systems. The transformation began quietly in the ruins of post-war Japan. In 1947, W. Edwards Deming was involved in early planning for the 1951 Japanese census, brought over at the behest of General Douglas MacArthur, who grew frustrated at being unable to complete phone calls without lines going dead due to Japan's shattered post-war economy. Deming was an American statistician who had worked during World War II as a quality expert in American armament plants. His expertise in statistical quality control had helped American factories produce military equipment with systematic efficiency during the war years. Now he was being asked to bring those methods to Japan's reconstruction. In 1950, Deming was invited by the Union of Japanese Scientists and Engineers to teach statistical control as part of Japan's reconstruction efforts. From June through August 1950, Deming trained hundreds of engineers, managers, and scholars in statistical process control and concepts of quality. What made Deming's teachings transformative was not that they were revolutionary in content. Statistical process control had been developed in America decades earlier by Walter Shewhart at Bell Laboratories. American factories had used these methods extensively during wartime production. The transformation came from Japan's receptivity to implementing these methods systematically across entire industries. Deming's pedagogical approach dovetailed perfectly with Japanese manufacturing needs and helped provide a philosophical basis for infusing quality as an intrinsic part of the production process. Most importantly, Deming was conveying these concepts on the eve of the electronics revolution, where unparalleled precision, cleanliness, and consistency of product were essential metrics determining success or failure. The timing proved fortuitous. Japan needed to rebuild its industrial base with limited resources. Quality control methods enabled factories to reduce waste and maximize efficiency when materials were scarce and mistakes were costly. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.